Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest in the Data Science Central webinar series. I'm your host, Kurt Cagle, and I'm the community editor at Data Science Central, a tech target property. I'd like to start our event off today by thanking TigerGraph for sponsoring today's event. TigerGraph is a longtime supporter of the Data Science Central community, and we are honored to have them sponsoring our event today. Our webinar is entitled Knowledge Graph and Machine Learning, 3 Key Business Needs, 1 Platform, presented by TigerGraph. Before we begin, I'd like to briefly review the format of today's webinar. Today's event will be 1 hour long. We have one presenter, who I'll introduce in just a minute. There will be a 10 to 15 minute Q&A following the presentation. And this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We will be reviewing and presenting them on your behalf during the Q&A portion of today's event. I am very pleased to introduce today's speaker, Dr. Victor Lee. Dr. Victor Lee is a head of product strategy and developer relations at TigerGraph. Victor brings together a strong academic background, decades of industry experience, and a strong commitment to quality and serving customer needs. He was a circuit designer and technology transfer manager at Rambus before returning to school for his computer science PhD, focusing on graph data mining. Victor received his Bachelor's of Science in Electrical Engineering and Computer Science from UC Berkeley, a Master's in Electrical Engineering from Stanford University, and a PhD in Computer Science from Kent State University. He was visiting professor at John Carroll University before joining TigerGraph. Thanks for being with us today, Victor. We're looking forward to your presentation. The COVID-19 pandemic has accelerated the pace of digital transformation across all industries. Organizations are looking for ways to accelerate their analytics, AI, and machine learning projects to increase revenue, manage risk, and improve customer experience, especially for online channels. Knowledge graphs combined with machine learning are driving 3 key data science capabilities to deliver the business outcomes organizations need. First, these are connecting internal and external data sets and pipelines with a distributed graph database. For example, UnitedHealth Group is connecting 200 plus sources to deliver real-time customer 360 to improve quality of care and to deliver call center efficiencies. Xandr, part of AT&T, is connecting multiple data pipelines to build an identity graph for entity resolution to power the next generation AdTech platform. Second, analyze connected data for never-before insights with advanced analytics. Jaguar Land Rover has accelerated supply chain planning from 3 weeks to 45 minutes, reduced supplier risk by planning by 35%, and is driving 3 times the business value from the data. Third, learn from the connected data with in-database machine learning. Intuit, as an example, has built an AI-based customer 360 with in-database machine learning for entity resolution, personalized recommendations, and fraud detection. Knowledge graphs combined with machine learning is central to Intuit's transformation into an AI-driven expert platform. In today's data science webinar, we will share design considerations and deployment best practices from these case studies by combining knowledge graphs with machine learning. Victor, with that, I'm going to turn it over to you. You can begin as soon as you're ready.
Thank you, Kurt, for that introduction. I'm very happy to be here with everyone today. And we're going to kick it off with a simple question, poll question, which you'll be able to see on your online interface. You can enter your answer. Are you using graph analytics now? And 3 simple choices: no, not yet. Or yes, you've investigated them now or in the past, but you're not using it in production. Or you are using graph analytics in production. And we'll just give you another 10, 15 more seconds to answer, and then we'll take a look at the results. Okay, So you see we have a variety of different responses, and that's normal for this sort of webinar. We're happy to address all of you. I think we have something here for everyone today. So as Kurt said, the title of today's presentation is Knowledge Graph and Machine Learning, 3 Key Business Needs, 1 Platform. And first, I'll tell you a little bit about TigerGraph, the company I'm from. We provide advanced analytics and machine learning on connected data. And that is through the only scalable graph database for the enterprise. So a graph database, like other databases, is for storing and querying data, but the data is organized in a way that it really highlights the connections between things. And as a benchmark performance, we are about 40 to 300 times faster than our competitors on several key measures. And this capability to both handle a lot of data and to do analytical workloads is foundational for AI and machine learning solutions. We can handle both OLTP, transactional, and OLAP, analytical workloads. And our query language, GSQL, is based on SQL, so it's easy to learn, but it's also enhanced for graph operations and for analytics. You can run the software installed on premises, or you can run it on the cloud, available through the 3 major cloud platforms, Google, Microsoft, and Amazon. Our customers include the largest companies in finance, healthcare, telecom, media, and utilities. Plus, we have several innovative startups in cybersecurity, e-commerce, and financial services. We were founded in 2012, and our headquarters are in the San Francisco Bay Area in Redwood City. So that's who the company is and sort of what our mission is. But let's talk about the capabilities again a little more deeply. So first of all, we handle data in a graph fashion, and it's a distributed graph database, meaning that the data can expand to multiple servers. So a graph database connects all data and pipelines easily and efficiently. And this is benefiting companies like we mentioned in the introduction, such as UnitedHealth Group and Xandr, who provides marketing analytics for AT&T family of companies. Second, you can do the analytics, right? So now you have the connected data, but you have to be able to use that data. And we mentioned we're, 10, 20, 30, 100, maybe 300 times faster than other graph databases, depending on than other databases, but we're also faster than non-graph solutions. And that's really the compelling case. Why do you want to use a graph database? It's because you can analyze the connected data. And 2 key use cases we'll talk about are, we'll focus on Jaguar Land Rover today. We'll also mention China Mobile briefly. And third, to do more advanced analytics or machine learning, to not just run some formulaic analysis, but to do intelligent self-learning algorithms. And that's something that, for example, Intuit is doing. And each of them is getting new business value that they wouldn't have had before out of this. If you look at the evolution of databases, for decades, the landscape was dominated by the relational database, which everyone knows. You have tables with rows and columns, and the tables at the design level, you think they're connected, but it turns out that actually to see how one table is related, there's actually no direct connection. It's just that 2 tables will have corresponding entries, and you have to search through both tables to find out where they have those corresponding entries. That's called doing a table join, and table joins, for that reason, they logically make sense, but in actual implementation, they're slow. So you have a clear but rigid schema, great for ordinary transactions, not good for analytics. Next, the so-called NoSQL era, which we have key value databases, we have wide column databases, we have document databases. Each is a little bit specialized, but if you look at the key value, that gives you maybe the best example. It's simple, and it's designed. Why were these created? They were created because they scale better than relational databases, but there is a cost. They do more basic things. You know, it could do a targeted thing like a document database. Key value, it's stripped down. It doesn't really do very much. It's just you give it an ID, it stores data. Now, the graph database, which first came along maybe 15 years ago, but it's really taken off in the last 2, 3, 4, 5 years. Again, data is organized as entities and then the connections between those entities. So let's say nodes and links, or nodes and edges. And the edges can have names and properties which give it semantic meaning. And so the schema is much more flexible, but the real key is that following the connections, analyzing the connections is much higher performance. So it actually, you can do the same things you do in a relational database with similar performance, plus you get the high performance connected analytics. And so that's the real power of graph databases. So again, you get richer, smarter data because you're representing connections as data. You have the entities, you have the nodes, and you have the edges, which are another form of data, and it easily connects different data sets, breaking down your silos. You can ask deeper and smarter connections because you can look more efficiently across the data. You can basically, in the same amount of time, the same computational resources, you can accomplish much more sophisticated questions. You now also have available to you graph algorithms and graph-enhanced machine learning, which we'll talk about today. And when you do that machine learning, because the graph is semantically understandable, the relationships have meaningful names to users. If you build your model based on these relationships, you get explainable results. You also get visually understandable results. 2 pluses. So let's start off by talking about business need number 1, connecting your data. Seems very basic. So start off talking about Optum or UnitedHealth. So their goal, of course, is just because they have so many data. They're one of the largest healthcare insurers in the United States. They have many data sets from sometimes started in-house, sometimes from companies they acquired. They need to integrate these. They need to do entity resolution. They need to be able to see across all that data at the same time. So they took 200 different data sets and pipelines. They started off, their initial project is sort of what they call member, what you might think of as the patient, integrating the information about the patient. So they get all their records, all the information, all the procedures they've had done in one place. And then, of course, you add some analytics. What they added was find similar members. Once you see the patient journey over time, the different types of activities that this member has experienced, we see there are a couple red flags. They want to see who has had similar history and similar red flags. You just click a button, and in 50 milliseconds, it can search 200 properties across tens of millions of patients to give a list of similar members. And so that is enabling their providers to provide better care, answering questions better for the patients. So they're both lowering cost and providing better care. I'm going to move on to the second case, and this is for Xandr. And what they wanted to do was entity resolution of people and households. So again, Xandr represents AT&T family of companies. I think you now have Warner Media. So you see at the bottom of here all the different types of digital devices that way people now engage with their content. They have the mobile phones, they have their laptop computers, they have their smart TVs, and they have their tablets. And people, depending on how they're accessing, they may actually have a different login ID. the device is using different technology. So first of all, the first task is to merge all these into one human user. And then the next level is to look at more than one human user may belong to the same household. And so part of it is they, again, are integrating data from multiple sources, some of it in-house, some of it external data, which they're trying to merge in, to try to understand who are their customers, what are their needs, and what are their interests. So they're gaining efficiency to both understand the household and the consumer usage, and to understand the limits they place on their technology, the different tiers of service they offer, so they can reach more people through the linked devices, and that they can provide lift. That is, when they're trying to upsell people, they can have a higher success rate because they understand the customer better. They know what they're using. They can infer what their interests are, and they're better able to convert opportunities into actual business. And so from the customer side, they're getting better recommendations. They're getting more personalized service. Also, they're able to apply privacy policies better because they are seeing the user's full engagement. So they make sure that they apply the same policies to all the devices. As I said, they are integrating both their own direct first-party data as well as third-party data. And it's a technical process. They normalize and curate the data. They assemble it into a graph. They do the graph identity resolution, again, to connect the users and the households, devices to human users to households. They do consent filtering to, again, do privacy or, child filtering, various things like that. And the result is their intelligent identity graph. Again, this is just showing another illustration of the tiers of information, a very high-level view of how they're integrating things, and how they have different IDs. There are subscription IDs, household IDs, device IDs, and these subtype properties, cookies, etc. So lots of information that needs to be integrated. There is, they use some AI to do the entity resolution, but the result is once they have that identity graph, just connecting all of that is very valuable to them. And they talked about how can this scale. Currently they have a distributed graph with 5 billion vertices and 7 billion edges. They do over 1 million daily updates from external information. And then they do a billion updates internally by running algorithms and creating new edges. So they analyze the data, they see a new relationship, and they add an edge to the data. So they have the initial external data. It gets frequently updated at large scale. And they also analyze to through the analysis, update the data. They run algorithms, and they also plan to scale horizontally, something that one of the reasons why they chose Tiger Graph is because of the ability to scale out. So again, I'm going to skip over some of this detail due to the time, but you can go back and read this slide in more detail, talking about the business case. I think we already went through a lot of information. This just provides a summary. So next, I'm going to talk about the second need, to analyze your connected data. Now, of course, we already mentioned some of that before because nobody wants to just store data and then never look at it again. These people have current operational needs. They're bringing the data together so they can use it right away. So first, we're going to talk about Jaguar Land Rover, well-known auto manufacturer, and they've been in business for decades. They obviously have gone through many business cycles, and they're still a thriving concern. And that's because they've been able to keep up with technological changes. And one of those is to really bring their supply chain analysis up to date. So they wanted to answer critical business decisions with the way that manufacturing is done in modern times, where we're doing just-in-time delivery has been around for a long time, but also users expect more customization. They expect to be able to pick the product they want and get it. And suppliers, manufacturers, top-end manufacturers like Jaguar, Land Rover are negotiating better deals with their suppliers to, again, be more flexible to get exactly what's needed. So there's many issues they need to do to optimize their operations. What they wanted to do was build this multi-tiered graph, which is connecting their end product, which are vehicles, cars, with the features. So, you know, one car has however many features. If you dig down, it's probably at the consumer level, there are several dozen features. If you go into the fine detail, there are probably hundreds. And then that translates into parts. And this is probably get into the hundreds of thousands of parts. And then the suppliers, who is providing those parts. And so through this multi-tiered graph, they are showing the dependencies between the different layers. And they're also including costs and constraints. And those constraints, which we'll talk about a little bit more, are very important for optimization. And so by building this graph and asking and getting the answers to the questions they want, they're able to identify and then reduce supply chain risks. So some of the questions they might ask, you know, demand for the Evoque model is suddenly surging in the US market. Do they have the parts they need to meet that demand? And what are the supplier side risks? So the basic procedure, you browse the graph to identify all features for Evoque. That's actually a very simple graph operation where you start the Evoque and you just propagate through the edges. So that in principle is very simple, but due to the size of the graph, that could take quite a while. In TigerGraph, it's very fast and efficient. For each feature, look at the parts needed, and then to identify the suppliers needed, and then look at things like just the fan-in and fan-out patterns. And fan-in is just looking at how many and who is connecting on the inside, and fan-out similarly, who and what are the details of the connections on the outside. And this is where I talked about costs and constraints, such as delivery time, such as what is the rate at which that producer can change their supply. If you tell them you want an increase, how long will it take them to produce that? Can they even do it? And what does their contract say in terms of how much of a premium would they have to pay? On the other side, there's often minimum payments they have to make. It says, you're gonna purchase this much from us regardless, whether you actually consume the 100,000 parts, there's a minimum you pay. So there are constraints on both sides, both on the minimum and maximum. And then there's looking at external shocks. What if there is a strike, et cetera? How can you minimize the risk? So all of those analyses are important. And then here's another side. So what if the demand goes down? You now have a surplus. Can you redirect that surplus to help make a different vehicle for which there may be better demand? And so that's where, again, the connectivity of this graph is very powerful. It's very easy to see where's the overlap in parts between two different vehicles. When you take that to the planning stage of not just sort of tactically seeing what do I do because I now have a surplus, you can actually, again, more clearly look at planning. How can I design my vehicles so that they in fact use more of the same parts and that there's less risk? And one of the things that JLR really liked about TigerGraph was the ability to easily search up or down, going from parts, searching up, well, you could say, in this case, up to features in cars, or searching down to suppliers. A lot of the other platforms, tools they looked at did not allow them that bi-directional search. It's very easy in TigerGraph. And again, finally, we get to the optimization problems. If you know some about the mathematics here, you know that finding the perfect solution is very hard, but there are methods to try to get good, realistic estimates. But even those were too computationally expensive for their platform they were using. And this is where they get to sort of their signature remark. And I'm not sure if it was saying it here, but they said, for example, one analysis that used to take them 3 weeks, they could now do in 45 minutes. 3 weeks is not a real-time decision. You cannot, that's not much of a response to just run the analysis. If it's taking you 3 weeks to decide what to do, you may have already lost the opportunity. 45 minutes is a different world. Now you can make real-time decisions. So decision speed, 120 times faster, overall business value, 3 times increase, and supplier risk drop of 35%. So from a business perspective, this was a huge win. Graph analytics, scalable graph analytics was the answer. Again, there's CEO, again, talking about queries across the supply chain now take 30 to 45 minutes compared to weeks when they were using a SQL relational database. So again, that's highlighting the difference between the relational architecture, which we know and love, versus graph databases. The problem can be addressed. On paper, it looks like it should work, but if you look at the actual performance of the products, that really graph could be your only way these days. We're going to move on to our third capability now, and that is to do more advanced analytics or machine learning. And we've talked about this in other webinars. We're just going to do a summary today. But we're going to start with a very easy to understand business need to cut down on fraud. Fraud costs the global market $30 billion a year. That's not including money laundering. That's just straight fraud. And unfortunately, it can be hard to detect. And because of that, companies try to put in their policies and filters to prevent fraud, but sometimes the tools, the policies and procedures they're too rough. And so what they end up doing is they end up preventing a lot of transactions that were legitimate. So the estimates is that 80% of blocked transactions are in fact non-fraudulent. So that's a lot of lost business. So, a lot of this may be retail business, such as through a credit card. It could be loan applications. It varies in every sector. But if you look at the credit card industry, they have like $118 billion of blocked sales in the US. And each year, 15% of cardholders experienced at least one blocked sale. It's even higher for higher income consumers, those who make $75,000 or more per year. They see 22% of them had at least one transaction blocked. And 40% of those blocked transactions were trying to make a transaction of value of $250 or more. And you can understand the logic there, that the businesses, they're more concerned about the bigger ticket purchases. They don't want to make a mistake there, so they're being more conservative, so they're blocking more transactions. But unfortunately, they're blocking a lot of legitimate transactions and losing business. So let's look at an example of how you might or might not detect fraud by looking at it from a graph-based perspective. And what we have here is we have a customer on the left who has a credit card account, and it's associated with a certain phone number and email address, and that represents the card itself. Fine. Excuse me. And then they try to make a payment. And excuse me, they are using their iPhone. Maybe we should update that iPhone 6. I think we're up to 12 now. But so when they first set up their account, it was an iPhone 6. And it's linked to the account. It uses that same phone number. So far, everything looks good. And they're trying to, the money is going to this other account, which was set up by this customer. So starting from the customer and that account, we have, start from the account, we have 3 so-called graph hops. And so far, everything looked good. But if you look deeper, that customer has this phone number, which was used on this device. And in the past, excuse me, there are transactions on record which show that this device and that phone number are associated with a stolen credit card. And so if you trace through the graph deeper through 6 hops, you can see that actually this is suspicious because this person is closely associated with a stolen credit card. So if you look deeper enough, you might deny this transaction. On the other hand, if you look this deeply and don't see any red flags, then you should actually permit it, even if it's a bigger ticket item. So we want to both block the real transactions, get the true positives, and allow, block but allow the good transactions. So we don't want to have false positives of fraud. And that's sort of, and take a quick look again at this, how this looks graphically. 6 hops, we have accounts, payments, persons, phones, devices. We have about 5 different types of entities. In a graph database, you'd have like at least 5 different tables. The transactions themselves would be another table. It could be done, again, but probably not in real time. The performance would be too slow. So again, this company, they had 20 terabytes of data, and they need to be able to compare known fraudulent credit card applications with the ones they're being presented with. So they have a large scale, and they need an answer quickly. So by pairing this sort of deep graph analytics with, there's some additional learning, which we haven't talked about, but they're trying to understand how do you deal with the different rates, the probabilities. If you see a connection, what is the probability that is problematic? And that's where the machine learning comes in. And so based on the loan application fraud prevention, they got a 30% uplift and $15 million in annual incremental fraud avoidance. So they're preventing $15 million of fraud, and they're saving $1.5 million through business they're allowing. And this was all went into production in about 3 months, and in the first year saved $16.5 million. This is maybe a little hard to read, but this is looking at the list of properties that when you look at the data and try to see what sort of characteristics of the data can I see from the non-graph data, just looking at the data as tables, they had about 4 properties they're looking at: the amount of the transaction, who is the customer, who is the merchant, and what is the merchant category. But when they looked at the graph data, then they have much more relational properties. and he had a list of 16 properties. So they have a richer set of properties to work with. And that's one of the fundamental things about using graph for machine learning. Machine learning, or supervised learning, for those of you that know a little bit more, you take training data where you have entities like customers or transactions, and each of those has properties, which we call features, and you need some examples where some historical data where you knew if I had this customer doing this transaction, that turned out to be fraud. You have all these other cases where it turned out not to be fraud. So that's called tagging or labeling the data, whether it's fraud or not. And you want to have a good set of features to associate with the target results, in this case, fraud or not. And the more features you have and the more appropriate features you have, the better, a more accurate machine learning model you're going to get. And so that's why this is so powerful, to have more variables and more variables that are worthwhile. So again, in this analysis, it actually doubled the performance of the fraud detection system by reducing the false positives by 50%. And this next slide gives a little more detail about what we mean by those true positives, false positives. So this is called a confusion matrix. There are two different axes. One, I believe the vertical is saying, what is our prediction? Is it fraud or not? And the horizontal is the truth. Is it fraud or not? So this upper quadrant is where we predict it's not fraud, and it in fact is not. And this is the biggest case. Most transactions are not fraudulent. So we're not showing we'll show some numbers later, but this is the biggest category. Most transactions are not fraud. Some cases we predict, and they in fact are fraud detected. So, and these are the cases where we get it wrong. This is where we did not, a false positive. That's where we predicted, but it's not, and a false negative, where we didn't predict, but in fact is fraud. And so the ideal predictor makes no mistakes here. It has 0 false positives and 0 false negatives, and it categorizes these two cases perfectly. Nobody has that perfect system. But again, if we had this very simple system where we just permitted every transaction, and this was with some test data of, I think, is that about 120,000 transactions. In those 120,000, there are 1,320 actual cases of fraud. And if we have a simple system which just permits everything, then it will be wrong. It will get a false negative where it says this was not fraud, but it actually was 1,320 times. Now, if we look at just those 4 properties, non-graph properties, this is what we can do. We can actually predict about 80% of the actual cases, but then these cases, we made some errors. We either missed some fraud, or we falsely accused some people of conducting fraud. And this is when we add the graph features. So we've detected more of the real fraud cases. We have also reduced both the false negatives, and we've reduced the false positives. So there's only 55 cases where we blocked a transaction when it in fact was legitimate. So that's you can clearly see that this is the best balance of the overall performance. We're coming close to the correct number of actual fraud cases, and we have moderately low numbers, lower than this case where we didn't use graph. So graph was able to both improve the precision and the recall of those technical terms for fraud detection. And again, here's another customer doing a similar type of work. The previous one we looked at was loan applications. In this case, they're credit card transactions, which are a different type of loan. In this case, they used graph algorithms, in particular PageRank and the Louvain community detection algorithm, to help them analyze their data. So here's a very graphy thing. Previously, And in the previous example, we talked about graph features like, take a quick look here. Basically, these are mostly so-called one-hop relationships where we're relating one table to another. What's the total number of fraud detected per merchant, or what's the total value of transactions per merchant category? They're relating two things, merchants and transactions. Not too complicated, but PageRank is a full graph analysis. PageRank originally comes from trying to rank which are the most important web pages out of the entire World Wide Web. Louvain community detection is also a full graph analysis where it looks at your entire graph and tries to see how it should partition or group up things, sort of find these people are closely associated based on their connectional pattern. So these are both computationally intense. Really, you absolutely need a graph to do this. But again, they got a 35% uplift by improving their fraud detection accuracy, avoided $50 million of fraud, and again, $1.5 million in cost savings. So another case, first one, loan applications, and this one, credit card applications, both benefiting from scalable, real-time, distributed graph analytics. Both of those cases where they obtained graph properties first, and then exported the data to do their machine learning outside. So they learn the model outside, but since the model is based on graph properties, when you deploy the model, you're still using the graph. You're deploying in the graph. Now, there is another approach doing in-graph database machine learning. And that's where you do the training in the graph also. So, the basic idea is you have your database, you bring in your data, your operational data, your transactional data, your data about customers and about merchants. You connect that all to make your graph. Now, and there's the question, do you just figure out some features, run some algorithms here, some algorithms like PageRank, or do you do your machine learning algorithm in the graph? And the advantage of doing the machine learning algorithm in the graph is, quite simply, you don't have to export and import the data. You can always have access to the most up-to-date information. And again, you don't have to export and import running two different systems and worrying about the latency between those two. So maybe you're running a neural net type algorithm in here. Maybe you're doing some type of recommendation system, latent factor analysis. There are a variety of different in-graph database machine learning techniques. But once you do that, you again deploy it by, for example, a transaction comes in. You do an analysis of graph properties based on that user and that card. And you see what does the model say about those property values? The model basically is a set of weights and says, I get these values for this customer and I apply the different weights. What is the net score? Is this a go or no go? So if you want to do this, and this can be used for all sorts of different applications. It's not just fraud detection, but it's recommendation, it's intelligent entity resolution. And it's really because TigerGraph can handle this, because both our platform and our query language. We haven't really talked about the query language, but the query language is very important because you have to be able to describe these algorithms. Our query language is procedural. It has flow control. It has accumulation. It has pattern matching. You can describe machine learning algorithms directly in the language, as well as those PageRank and community detection algorithms can be written directly in GSQL. And so whether your platform is appropriate for in-graph machine learning, you have to take into account several factors. First of all, do you have the big data capacity? We all know you need volume, variety, velocity of data to get good machine learning predictions. So can you handle the large capacity? There are other graph data platforms that, from a storage perspective, they can store a lot of data. But it's really when you get to what can you do with that, that you start to see the differences. As I just talked about the G-SQL language's capabilities for implementing those algorithms, TigerGraph can. The other platforms, they provide really side tools. So again, you're not really doing it in the graph. Does it have native parallel processing? TigerGraph, yes. The others, maybe. And for parallel accumulation, and this is something that's really unique to TigerGraph, accumulation is something that really, if you know the MapReduce platform, if you know Hadoop, those are intended for efficient accumulation of doing bulk data, statistical analytical work efficiently. TigerGraph is based on that principle. These other typical graph database is not. So TigerGraph, again, distinguishes itself from the vanilla graph database in these different ways. Real-time deep link querying, the ability to handle 5 or 10 hops in sub-second capability. And that really comes from having done a bottom-up ground, from the beginning, designing a graph database from scratch in C++, native graph designed for parallel execution, and with efficient compressed storage, because that compression actually gives you cost and speed advantages. The ability to handle massive scale through a distributed architecture, massively parallel processing. And again, that compression actually helps you in multiple ways because it reduces the overall footprint where you can scale out, but you may not need to because there's more compressed data. Less data is moving around, which is sort of one of the Achilles heel that other systems have with distributed data. And then you get to the analytical capability. What does your language allow you to do? And what does the sort of built-in operations, what can your graph engine, how can it manipulate data? Is it really designed for analytics? And again, that's an area where TigerGraph excels. And lastly, to make it easier for end users to use the product, we've been introducing no-code tools. One, for bringing in your data from relational, so no-code data migration from relational database, and then a no-code visual query builder, because for some new users, graph is new to them, it's a little unfamiliar. Learning the query language, while it's similar to SQL, it is another step. But because graph is so visually intuitive, a lot of times you can just build your query visually by dragging and dropping balls and sticks together. So that's a great capability, a potential for graph analytics, something that TigerGraph is offering to its customers. So I'm wrapping up here. I want to thank Data Science Central and Kurt for hosting me here. We have several starter kits that you can use to test out this TigerGraph by itself or TigerGraph with machine learning. We have 4 different starter kits available on TigerGraph Cloud, which you can try for free. We also have our developer portal at dev.tigergraph.com. If you are more of a software developer, you may want to look at these. If you're more interested in building your own and you want to really learn sort of under the hood how some of this works, so I invite you to take a look at either of those. So again, thank you for your time. There's a lot more I could say, but I know we need to wrap up. I'm going to be here to answer some questions. So you can try TigerGraph for free. You can get the enterprise license. You can try our cloud service. And we have some of the presentations I talked about today were originally presented by the companies, by JLR, by UnitedHealth Group at Graph Plus AI World. And you can try TigerGraph in a bunch of ways. You can engage us at the community, and of course, you'll find us on social media. So thank you.
Thank you very much, Victor. Fascinating talk. I've got a number of questions to ask, some of which we'll cover now, and some I will probably save for afterwards. Anyway, so let's get into the next layer of this. We've got a number of questions to be able to work. Now,
sure.
First of all, what's unique about your capability to scale for large data sets or deep analysis compared to others in the industry?
Great. I think I'll go back to this slide, and maybe I rushed through it a bit, so I try to hit on the key points again. It's first, I'd say whether or not you have a lot of data, this first point is important. It's ability to, in a time with the speed and efficiency that the user needs, to follow as many links as they want to. And I think about it this way. You start out at one point in the graph, and you want to look at who are your immediate neighbors. If you think of it as a knowledge graph, then what you're directly connected to is what you know. And so with one hop, you can see, what do I know? Now, if some of those first connections are other persons or other entities, organizations, then the second hop is telling you, what do they know? And so with two hops, you find out not just what do I know, but what do they know? And then three hops, and so again. So each time, you're exponentially increasing your knowledge base. So the ability to see, you cannot analyze data that you can't see. And while it may seem surprising, but even following three hops on a large, well-connected graph is computationally challenging for some platforms. For TigerGraph, that's pretty easy. And that's why I say, we can handle, depending on the data and the query, we have customers who are doing more than 10 hops on a large data set in less than a second. And it's really how much data do you have available to analyze, and what sort of analytics can you perform? That's the most important difference. And that comes to how we were designed from scratch. And we just simply have not seen any other graph database in the market who's taken a similar approach and been able to perform in the same way. Scalability is another factor, but so these two, to go deep quickly and to scale out are the two key points. And those both due to the low-level design and architecture we used.
Okay. So you've also mentioned algorithms. How many do you have? How many algorithms are out there? And, of those, if you run into a situation where you don't have an algorithm that's supported directly by TigerGraph, what can you do? Or how can a customer make use of that?
Okay. So we have an open source graph algorithm library on GitHub. We currently have about 35 algorithms. We add more on a regular basis. And the thing that is unique about TigerGraph is that our algorithms are written in the GSQL language, and you can see exactly how they're written, and you can modify them and recompile them. That's different from how other companies work. For them, it's a closed function you just call, and you can't modify it. And that's usually because their platform, their database is not really designed for this type of workload. So they have to run sort of additional software on the side to get the algorithms to perform efficiently. So they have to do some special tuning to get the algorithms to work. It's not running in the database the same way that the regular querying works. For us, Algorithms run the same way that regular queries work. We show you everything you can do. So you get to the point, okay, what if you want a new one? We take requests from the community. We do our best to create one. But because the language allows you to, sometimes there's a very simple translation from how you see the algorithm written in, say, in Python or in pseudocode to how it ends up in GSQL. You could take some basic GSQL training courses, and you could write the algorithm yourself. So that's it. Either you could write it yourself, or we'll put it on a request list and do our best to add it to our GitHub library.
Okay, so let's talk a little bit about external data, because after several years of working in the data space, I know that you're always basically dealing with someone else's data. You talked some about importing data. What kind of mechanisms do you have for importing, and what kinds of data can you basically pull into TigerGraph?
Right. So what kind of data? So the most straightforward is structured or semi-structured data, which could be in a variety of formats. It could be if it's coming from files, it could be in CSV or JSON or XML. If you have more unstructured data like text, you're probably going to need to pre-process it in some way to kind of figure out how you want to break up. Do you want to break it up into words and with nouns and verbs, etc.? So that's the sort of. Or now, do you want to read it directly from some other data source, which is often common. You're taking data from a relational database, you're taking it from your data lake, or there might be the previous case. There might also be streaming data coming from a bunch of who knows what type of device you're getting it from. If it's coming from some IoT device, but if you're reading from a relational database, as I mentioned, we have this no-code migration tool. It's still in the beta phase where, and that's really because currently we only have built-in support for a couple different relational databases. But in the coming year, we're at the end of 2020, fortunately. In 2021, we'll be adding a lot more built-in connectors for a lot more relational databases, for a lot more platforms like Snowflake. We already have connectors to AWS S3, and we'll have one for Azure Blob Storage. Those are all options. Lastly, I want to mention Kafka. Kafka has always been part of our technology stack. And so that's a great way to have sort of a messaging pub-sub system where you can have your original source is pushing in data into Kafka, and then we will read it from the topic out of Kafka. So you can have this queuing system if you have streaming data. So Kafka, direct connectors to relational with more direct connectors on their way, and just a variety of different data formats that are supported.
Okay. So beyond GSQL, do you have support for any other languages?
Good question. The language platform right now, language landscape for graphs is where you have a couple different de facto or popular languages. We know there are a lot of Cypher users, which started from Neo4j and then expanded with OpenCypher. There was the Gremlin Tinkerpop Apache movement, which it's still there's still companies offering that, though we're seeing less growth there. And then there's TigerGraph GSQL, which is designed to be similar for SQL users. The future is GQL, or this is an ISO committee, which is defining a new standard. I actually am missing a meeting in this month in order to do this webinar. I'm missing a ISO meeting where we talk every month about forming a new industry standard. So all the major property graph vendors are planning in the next year or two to offer GQL and to provide a transitional path. So for right now, we offer GSQL. We just introduced some features expanding GSQL to be even more similar to SQL. So in some cases, you can directly write a SQL query. If you want to migrate from Cypher, we're happy to help you with that. Lastly, I want to mention that we're also building Python drivers and Java drivers so that rather than, and REST APIs. So if you don't want to use a graph query language, you can do it with REST APIs, and we are working on and have available, but are continuing to improve Python drivers and Java drivers and Go drivers, so you can just program in those languages and talk to our database.
Okay, interesting. So you talked at one point about supply chain, with especially talking about Jaguar and Land Rover. It's such a cool name, Jaguar. Yes. Anyway, one of the questions that I would have is, there's a lot of those supply chain management tools out there. How do you see Tiger Graph being different from what's out there, and where do you see that as being a potential selling point for the graph technology approach in general?
Yeah, that's a great question. Because, when I first saw that companies like JLR were interested in, I was actually curious. I believe in our product, but I'm no expert on what is currently available for supply chain. So I asked them, well, we know we're great, but why is it that those other ones aren't good enough? Because they've had decades to sort of optimize what they offer. And you have the idea that, they're built on, a lot of them, because they're older, they're sometimes built on older technology and have only made incremental changes. They also tend to be closed tools where they offer what they offer, and if it's not available in the product yet, it may not be easy to add it on. But it really came down to what is the database and the computational engine underneath the hood. People have been able to present something that looks like a supply chain, looks like a graph, but a lot of these original tools were not built on graph databases. And it's really the fact that it's built on a graph database, again, with the characteristics of Tiger Graph that we talked about, that it enabled it to perform these more complex analytics on larger databases. And again, what you need to see is that even what we presented here today about talking about the 4 tiers of cars, features, parts, and suppliers, that's only scratching the surface of what they're trying to do. They also have the orders coming in for different vehicles. They have the contracts and the terms of the contracts they have with their suppliers. They have the regulatory things, particularly operating in the European market. There are various things they have to follow. And these, from people who are used to operations research, from that approach, this is a constrained optimization problem. And they would also know that this problem, when we say computationally difficult, or we say intractable, it's NP complete. You cannot find the perfect answer in a reasonable amount of time. What you can do is find a highly good answer. And it's really the ability where we talked about the Tiger Graph engine having a graph database that's designed for analytics, you can do anything with it. So where JLR was running into problems was the existing tools they have, they weren't even using a supply chain tool. They were using relational database. It just couldn't address the questions they needed of trying to, what's the most vehicles? I'm trying to produce these, 8 different models with several variations of each model. What's the most optimal production I should make, given what I know the demand is likely to be, but I'm not positive what the demand is? That's a hard question. And, the current tools were not up to that.
Okay. All right. We're probably getting down to a little bit beyond, but a couple last ones. First of all, talking about features, and I realize that the machine learning features are very different from features in cars, but when you're talking about the machine learning and AI capabilities, what functionality do you offer to be able to identify features and to extract features? And, how does that also kind of tie in, kind of pulling two questions into one, how does that tie into explainability, which is a big issue?
Sure. There are about 3 different approaches you can take for features, for training your system. You can use what is shown here with a targeted approach. You can say you take a so-called domain expert who looks at the graph schema and knows the application, so they understand the semantics of what does it mean if I look, why would I want to count the average number of average transaction size? Or if you're looking at some other like healthcare, looking at what are the typical prescriptions that a doctor in this field would write, so they would understand what's an outlier. That type of prescription is not normal. You can have features based on that domain expertise. Another category is you can have features which use these generic algorithms like PageRank or Louvain community detection. And the third approach is you can do something like what's called graph embedding. And you may have heard of word embedding, which comes from natural language processing. But the basic idea is you have a graph. And the thing is, traditional machine learning algorithms don't run on graphs. They run on matrices and vectors. So we need to actually remove the graph structure and transform it into some linear representation. So graph embedding is actually an algorithmic technique in itself to have, you might call it, if you know something about this data science space, you'd call it dimensionality reduction. It is transforming the multi-connectional view down to, I'm not going to, rather than saying this person has all these connections which then connect to something else and then connect to something else, I'm going to approximate that as just a linear vector of saying I have 100 properties and those properties have these different numeric values. And a simple case would saying it's like a random walk. How many neighbors do you see in 1 hop? How many neighbors do you see in 2 hops? How many neighbors do you see in 3 hops? That's a very dumb feature vector that you could use for graph embedding. So graph embedding is another way of transforming your graph into data that the machine learning algorithm. So targeted features, algorithms, and graph embedding. The last one does not provide the explainability because those features, those numbers don't have semantic meaning. But both of the first two, particularly the first one, you're going to get the most explainability with the domain-based targeted features. You'll get good explainability with the standard graph algorithms, and you're going to kind of lose your explainability if you use graph embedding.
All right. That's fascinating, and I'd love to be able to get more into graph embeddings because I think that it's actually one of the more exciting aspects of the integration between machine learning and knowledge graph representations. Okay, so
I don't want to discount them; they're valuable, but it's a trade-off: explainability or the net result.
All right. Well, I wanted to thank you, Victor, for a superb presentation. And let's see. Let's move us on over to here. So, round of applause to our to Victor Lee for a wonderful, wonderful talk. Now, I would like to recommend for those of you who are regular participants of the Data Science Central series, mark your calendars for the December 22nd, 2020. The last of these presentations for the year for our next DSC webinar, which is going to be on data analytics and decision making, a neuroscience POV. And at that stage, we will be done with, I believe, we will be done with the DSC for 2020, which I think is going to be something that everyone will appreciate because we'd like to get done with 2020. Thank you very much. Anyway, so for those of you that haven't asked any questions that weren't answered today, we will be sending all unanswered questions to Victor and the TigerGraph team, so they can follow up with you after today's webinar. Additionally, today's taping will be available for on-demand viewing later and can be found in the homepage of Data Science Central in the Webinar tab located at the top of the page. Past webinars are available on demand at datasciencecentral.com. If you haven't had the opportunity to view them, I encourage you to take a look. There's some very fascinating subjects involved, and they provide very useful insight into a wide variety of topics of interest to our data science community. Okay, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks again to TigerGraph for their sponsorship, as well as to our speaker today, Dr. Victor Lee, for his superb insights into today's topic. Thank you very much, Victor, and thank you. My name is Kurt Cagle, and I'm very pleased to have been your host for today's event. I look forward to seeing you all again on December 22nd, 2020. Have a great day.